Aristotle was, to some extent, beginning to play the role of a scientist, but he didn't believe in mathematics. He didn't believe that the use of mathematics played any role in understanding nature. He never did use mathematics. And he had ideas we've had to unlearn, ideas about purpose, that if you really want to understand the meaning of something, you have to understand its purpose. And, you know, there is no purpose in the inanimate world. I'm not sure how much purpose there is anywhere else, but at least in the motion of the planets or the fall of a rock or the burning of a bush, there's no purpose. And it was important to eschew that way of thinking. Aristotle gave us many ideas we had to unlearn in order to make progress in science.
Physicists are somewhat in that position because we hope for a set of very simple laws of nature that will account for everything we see. But when we have them, there will always be a question, well, why those laws?
Exactly.
And many people say, in fact, a Jesuit has argued to me that that's where God comes in, that God ordained the laws and he is the ultimate explanation. And of course, the response to that is, well, you know, what have you really helped at all with that? What explains God? What explains why God is the way God is? If you have some specific understanding of that three-letter word, G-O-D, then you have the mystery. Why is God that way rather than some other way? And if you don't have any specific understanding of what you mean by, I hear the thunder, I hope he's not getting annoyed with it. If you don't have any specific understanding of what you mean by G-O-D, then what are you talking about?
Yes, quite.
Then it's just an empty word.
One science, however, and it was the most important one of all, that was the most developed, and that was the most practically useful, and that was astronomy. You might not think astronomy would be the most practical of sciences, but after all, it's astronomy that allows you to tell time, to tell directions on the surface of the Earth, to know what time of the year it is. And if you're crazy enough to believe in astrology, you can predict when planets will be in a certain position in the sky, which was very interesting scientifically, although in fact it didn't have the practical importance they thought it did. And that was the science that was developed mathematically to the greatest height. When Copernicus developed his theory of the solar system, it wasn't based on new observations. It was based simply on the work of the Hellenistic astronomers, just showing that some of the hand-adjusted features, the artificiality of the system of Ptolemy, could be accounted for by recognizing that we view the solar system from a moving platform, the Earth. But Copernicus used no new astronomical data. He used the data of Ptolemy.
It's a little bit like the explanations the Greeks were satisfied. You know, Aristotle explained falling bodies by saying they're going to their natural place, which is toward the center of the Earth. Well, when you say that, you really haven't learned anything more about falling bodies. It hasn't helped you to say that. And in the same way, talking about a God who is complex and created the world the way it is, you haven't learned anything. It doesn't help you to anticipate anything you'll discover in nature. Right. That in the end, we will not be able to explain the world. That we will have some set of laws of nature. We will not be able to derive them on the ground simply of mathematical consistency, because we can already think of mathematically consistent laws that don't describe the world as we know it. And we will always be left with a question, why are the laws of nature what they are rather than some other laws? And I don't see any way out of that. And I just regard it as just another one of the tragedies that we have to get used to, like the tragedy that we will die, and the tragedy, well, I don't want to linger on tragedy, but I think essentially the position of human beings is a tragic one. And the more we understand, the more clearly tragic it is. And part of it, which particularly affects a physicist, is the tragedy of never being able to come to a really satisfying conclusion of our questions, why? And what do we do in this tragedy? I think, well, Shakespeare showed us that one way of living with tragedy is to mix it in with comedy.
Yes, yeah.
And we can take a certain amusement at our position, always seeking why, never coming to the end. I think humor is one of the leavening agents that makes the tragedy of our position possible. There are other possibilities that are a little bit more recondite, and that have to do with the application of quantum mechanics to the whole shebang. And in quantum mechanics, you can, because the fundamental quantity in quantum mechanics is not the individual particle or billiard ball, but is something called the wave function that describes all possibilities. You can have a system where the universe has a particle in it, but the particle, it's indeterminate whether it's there or here, and both possibilities are realized, and it's only when you observe it that you see it's either here or there.
So maybe both exist.
Both do exist at the same time, and only an outside intervention collapses the wave function so that the particle is either here or there. It may be that the universe, the big universe, the whole thing, is some kind of quantum mechanical superposition of different possibilities. In fact, it almost certainly is, because we don't have any other way of... I mean, that's the best way that I can understand quantum mechanics, is that is the case. Some of our theories that describe what happened when the universe was 3 minutes old tell us the chemical composition with which the stars started. And that works too. I mean, the predictions come out right. There's a certain amount of hydrogen, a certain amount of helium, a certain amount of certain rare isotopes of hydrogen and helium, helium-3 and hydrogen-2, that we can calculate the amounts, and that's what we observe in the oldest stars. So that actually, more accurately, that's what we observe in the intergalactic material out of which the stars form. In terms of things we can actually observe, I suppose you could say we've traced the history of the universe back to the first 3 minutes. Earlier than that, it's just pure theory, except that these non-uniformities in the microwave radiation, which are so important, which we're studying with radio telescopes, and which we believe, and have every reason to believe, grew into the distribution of matter we see in the sky. These non-uniformities, we believe we have a theory for their origin in terms of a pre-Big Bang phase called the period of inflation. And it works. That is, it predicts certain properties. For example, the strength of the fluctuations as a function of how large they are. What's the probability of seeing a fluctuation this big as compared to one that big? That theory works, and it deals with a period of time which is incredibly early in the history of the universe. So early that you really begin to wonder whether there really was a beginning, or should you even talk about a beginning. I mean, it's so... I don't even know how to say how early it is, but it's way earlier than the first 380,000 years or the first 3 minutes. It's an incredibly small fraction of a second after the beginning, and those theories seem to work. But you know, that's only going back so far. Then you have to go back to what started inflation, what started this inflationary period, and we have theories. There are some attractive theories, but they can't be tested. We don't have any observational handle on them. An awful lot of people also
believe it doesn't matter whether it's true. You have to be religious because that will guarantee good behavior. You know, the wonderful line of Gibbon's about the pagan religions, he said, in the multitude of gods, Gibbon said, the common people found them all equally true, and the philosophers found them all equally false, and the magistrates found them all equally useful.
Oh, yes.
And I think many people in America and undoubtedly in Europe are in the position of the magistrates that Gibbon was talking about. They find them useful. Although I really don't think that, I don't see religion as actually inspiring moral behavior. In fact, you very often hear people say, well, these people who blow themselves up for some religious reason in the Middle East, or Hindu mobs who destroy a mosque, or Muslim mobs who kill Hindus, or that they're not really religious, that real religion doesn't involve that kind of behavior. I think what they're saying is that they have a moral sense which allows them to distinguish what is religious from what is not religious. I think, for example, George Bush said that these terrorists have hijacked a great religion. So, because their actions, their terrorist actions, don't fit his idea of religion. You see, what's really happening there is that instead of using religion to decide what is moral, they're using their moral sense, which fortunately is a perfectly good, reasonable, enlightened moral sense, to decide what is religious. And if that's the case, then what's the point of the religion?
Finally, I wanted to know whether there were any particular reasons, apart from being constantly asked by people like myself, why Stephen felt it necessary to address himself to the topic of religion more than many of his colleagues did.
Oh, I try not to do it too much. You know, I don't want to become the village atheist, and I do get involved in a lot of other issues like missile defense and post-constructionism, neo-modernism. But I do spend probably a little bit more time than I should on religion, and I have a certain amount of hostility to it. I think the most rational reason for it is because of the harm that I see it does. We were talking about that earlier. Many people do simply awful things out of sincere religious belief, not using religion as a cover, the way Saddam Hussein may have done, but really because they believe that this is what God wants them to do, going all the way back to Abraham being willing to sacrifice Isaac because God told him to do that. Putting God ahead of humanity is a terrible thing. Plasma physics is driven to a large extent by the practical need to understand, well, some astrophysical phenomena, but also to try to make thermonuclear fusion work. And so the plasma physicist does not search for mathematical beauty. In fact, my friend runs away from it. But when the aim is not practical but conceptual, when you're trying to understand why we live in the kind of world we do, the kind of theory that is going to be useful to us would be a theory that has great mathematical beauty, because it's only in that way that it could have explanatory power. If it's ugly, that means it has a lot of various discordant elements, and you haven't really explained much, because you have to say, why is it that way and not some other way? You haven't gotten very far. Whereas if it's beautiful, you have a feeling, this explains it. Even though the beauty may itself be a consequence of something much deeper, which doesn't have that particular kind of beauty, may have some other kind of beauty. So that's another thing. We look for theories that are beautiful. And there is a hope that at the very bottom, there will be something completely beautiful.
I think I've heard you say, all right, that many physicists, going back to the God question, don't really care. I mean, they don't think it's an interesting question. I can't quite get that. I mean, it does seem to me that, I don't believe in God, but it does seem to me that you've got to care about it, because if it's true, it's one of the most
important thing in the world.
Yes.
That's right. I agree.
Yeah.
Well, I think the expression I used is that most of my friends in physics don't care enough about religion to qualify as practicing atheists.
Yes.
They just don't care, and they don't want to think about it. And I do think about it. I try not to think about it too much. I mean, clearly one could let it run. I mean, you could let it run away with you. I've visited organizations of people who are atheists and who gather together for mutual comfort.
Yes.
To me, it smells a little bit like a church.
Yeah, they're not very edifying, some of those meetings, are they?
But I mean, they're very well-meaning people, and
Yes.
I agree with them, but I wouldn't build my life around.
You go along to give them a bit of moral support, but
Well, they invited me, so I
Yes.
went. But and I think maybe you and I have also some slight difference in our attitude toward religion on the aesthetic level. Well, perhaps not, but it's been part of our lives for so long. So much of
yes.
history has been
Yeah.
bound up with it that you can't not only be interested in it, but have a kind of respect for it, the way you would have respect for someone who you don't particularly like, but who's still very powerful and has played a large role in your life. The question, why are the laws of nature what they are rather than some other laws? And I don't see any way out of that, and I just regard it as just another one of the tragedies that we have to get used to, like the tragedy that we will die, and the tragedy, well, I don't want to linger on tragedy, but I think essentially the position of human beings is a tragic one, and the more we understand, the more clearly tragic it is. And part of it, which particularly affects a physicist, is the tragedy of never being able to come to a really satisfying conclusion of our questions, why. And what do we do in this tragedy? I think, well, Shakespeare showed us that one way of living with tragedy is to mix it in with comedy.
Yes, yeah.
And we can take a certain amusement at our position, always seeking why, never coming to the end. I think humor is one of the leavening agents that makes the tragedy of our position possible. I would say a beautiful theory is one that doesn't have arbitrary assumptions, that isn't carefully tinkered with to make it match observations. And this is not, to me, as beautiful as a theory which is so logically constrained that it can only be one way. But we don't necessarily get all the beauty in life that we hope for, and you can't reject a theory just because it isn't as beautiful as you were hoping for. It's not entirely ugly to imagine that the answer, that the question why things are the way they are is answered by saying that they are that way just locally, and that they're different in other places. For example, the question why the Earth is 93 million miles from the sun, a theory that doesn't predict that might be regarded as an ugly theory because it becomes an arbitrary number. On the other hand,
it's real.
On the other hand, if there are billions of planets, as in fact there doubtless are, and they occupy a complete continuum of possible distances from their parent stars, then you would say that the beauty is, and perhaps there is a theory that describes the statistical distribution of the distance of planets from their stars, that says what is the probability of having a planet of a certain mass, a certain distance from a star, that might be a beautiful theory, even though it doesn't say anything about where any one planet is from the star. So we might have a statistical theory of multiple universes, which would be in its way beautiful, although it doesn't explain why any one universe is the way it is. And very often the beauty we find in nature is of a statistical kind. For example, the theory of thermodynamics is universally regarded as a beautiful physical theory, but doesn't tell you where each particle is in a gas. It just tells you statistical things about that. You search for beauty, but you can't be too sure in advance where you'll find it or what kind of beauty you'll have. But in the end, if the theory isn't beautiful, the hell with it. It isn't worth it isn't worth worrying about. And that is in the method of approach to truth. Religion largely relies on authority. It may be the authority of sacred texts, as in Sunni Islam and Protestant Christianity, or texts together with religious leaders who are divinely inspired to interpret them, like Shiite Islam and Roman Catholicism. We don't have anything like that in the world of science. And I want to make a clear distinction. We do have heroes. As scientists, we have enormous respect for. But they're not authorities to whom we go for solution of scientific problems. For example, in my field, certainly Einstein is the greatest hero of the 20th century. But no one today arguing about the theory of gravitation would settle the issue by referring back to Einstein's papers of 1915, 1916. Today, it's understood that any reasonably good graduate student understands general relativity better than Einstein did. We have learned, we have progressed, and so in science we don't have prophets. We have heroes, but not prophets. And I think that another difference in the approach to truth is that we try hard in science to stamp out the influence of wishful thinking, whereas so much of religious thought seems to be nothing else. I must believe in the afterlife because how could I face it if my life was going to terminate at death? The one thing that science cannot do, however, any more than religion can, is to justify itself. As David Hume understood long ago, you cannot use scientific arguments as a justification for science itself because that's circular. It's a moral choice between the methods of approaching truth of religion, the reverence for authority, the search for beliefs that will make us happy, and the more austere, self-reliant approach to truth of religion. For me, the moral choice is clear, but it is a moral choice, and one that can't be, I think, argued about rationally. So what do we do about this conflict? There are those whose views about religion are not very different from my own, but who nevertheless feel that we should try to damp down the conflict, that we should compromise it. For example, Steve Gould, and he can correct me if I'm wrong because he's here, Larry Krauss, feel that it's most important to maintain the integrity of scientific teaching, and we should try to enlist the mainline religions who are often perfectly comfortable with teaching Darwinism, say, in school, as our allies, and not step on their toes by talking about a confrontation between science and religion. Ed Wilson, another dear friend, wants to enlist the mainline religious denominations as allies in the defense of the environment. I respect their views, and I understand their motives, and I don't condemn them, but I'm not having it. To me, the conflict between science and religion is more important than these issues of science education or even environmentalism. I think the world needs to wake up from its long nightmare of religious belief. And anything that we scientists can do to weaken the hold of religion should be done, and may in fact in the end be our greatest contribution to civilization. Thank you. I think there are things that are truly strange, and that even though we can deal with them mathematically, we shouldn't lose the sense of strangeness. Not relativity, which no longer seems to me paradoxical or weird, but quantum mechanics is really strange. The interpretation of quantum mechanics that developed in the early 1930s under the leadership of Niels Bohr in Copenhagen, the Copenhagen interpretation, I think is fundamentally flawed. It divides the world into physical systems and observers.
Yeah.
And that can't be right. Observers are parts of the world. They have to be described by the same quantum mechanical language as everything else. There is a hope, which I nurse, but I don't see being realized, that eventually we'll find that quantum mechanics as we know it now is just an approximation, and that when an electron, which is in a superposition of states in which it's spinning this way or this way, when it interacts with some big thing like a physicist, a macroscopic body like a physicist or his apparatus, actually there is a physical decay of the wave function into a wave function where the electron is purely moving this way or purely moving the other way. And that in fact, the history of the world has not split. There has been an evolution of the wave function, which is not the kind of thing that occurs in quantum mechanics as we know it, but represents something that's specific to large bodies. I think some people have thought that perhaps gravitation has something to do with this, that after all, large bodies are the only ones where gravity is important. Gravity is an incredibly weak force on the atomic level. That would make sense of the whole thing, if that were true. But it requires a modification of quantum mechanics. And there are papers that suggest possible modifications of quantum mechanics.
Well, that's a great hope, isn't it? That would be wonderful.
I think that's the best hope, that we will find out that quantum mechanics, as we know it, actually breaks down for very large things. Now, it's true that the predictions of quantum mechanics have been verified for electrons that are separated by macroscopic distances. We can verify that there really is what's called an entanglement, that you can have two electrons that are meters away from each other, where the physical state is not a state where one is up and the other is down, but one which is a superposition of left up, right down, and left down, right up.
So these two particles know about each other.
Yeah, and it's just what you expect quantum mechanically, and it happens over macroscopic distances. But they're still just electrons. They're not big, heavy things with gravitational fields. So it may be that these experiments that verify quantum mechanics at macroscopic scales don't really settle the argument. But I tell a story in something I wrote, a true story, that a friend of mine who was a physicist at the University of Texas, who now incidentally wound up at Oxford, Philip Candilis, was standing next to me waiting for an elevator. And I asked him, whatever happened to so-and-so, mentioning a graduate student who would seem very promising and then we never heard of again. And Phil nodded his head sadly and said he tried to understand quantum mechanics. Well, the anthropic principle stated boldly is that things are the way they are because otherwise we wouldn't be here, and that, which sounds sort of nonsensical and
Trivial.
yeah, well, either trivial or nonsensical. If you say trivial in the sense that you just take the fact that we're here as an experimental fact, that's trivial. If you say that we take the fact that we're here as an explanation of why things are the way they are, not just as a casual observation, then it sounds nonsensical or it sounds religious or something. To some, there may be just some misunderstanding that some people may think that we're taking the anthropic argument as a fundamental hypothesis, that we think that the laws of nature have to be fine-tuned to make us possible as some kind of principle of universal benevolence. And I don't look at it that way at all. Others regard it, and I think this has a good deal more justice to it, as a retreat, and it is a retreat. I would love to throw the anthropic principle out the window and tomorrow sit down and calculate the value of the vacuum energy from first principles and publish that in physical review letters. And I can't imagine much else that would make me as happy. And not being able to do that represents a retreat. But we have to accept that, just as we had to accept that we will never calculate the distance of the Earth from the sun from first principles, that we have to regard that as just an environmental accident with a bias factor due to the fact that living things are on Earth to ask the question. In the same way, we may have to accept that we will never be able to calculate the energy in empty space, and indeed many other things, from first principles. And that would be a pity. And I would love it if that were not true. I would be the first one to celebrate the demise of the anthropic principle if that came about through the discovery of a theory that allowed us to calculate all these other things. And I don't think we should give up looking for such a theory. I don't think the idea of the anthropic principle should make us content or should stop research in other directions. But it is a possibility we may have to face. It's not logically absurd. Given the context of a multiverse, it is just common sense. We don't know there is a multiverse, but there are suggestions of it from other ideas. And if it turns out to be right, then we will have to live in this kind of world in which we have a diminished capacity to calculate things. Science has historically downgraded human beings from a central role in creation. Nobody cares whether the Earth is a sphere, but they cared very much that it's not at the center of the universe. After all, this is the stage of a great cosmic drama of sin and salvation, and shouldn't it be center stage? As we learn more and more about the universe, science sees less and less sign of any special role for human beings, either in the laws of nature themselves or in the history of the universe, of the sort that's imagined by traditional religion. First, there was the discovery that the Earth is not at the center of the solar system. Then the solar system is not at the center of creation. It's just one of many in our galaxy. Our galaxy is not unique. That was discovered in as late as the 1920s, that the universe has billions of galaxies extending in all directions. And just in recent years, through developments in the theory of the very early universe, in particular the theory of chaotic inflation due to André Linde, we now have a picture which is, I would say, plausible but not yet well established, that our Big Bang, this enormous firmament of galaxies expanding in all directions, is just one episode in a much larger multiverse in which big bangs, or maybe I should say not so big bangs, are popping off all the time, world without end. If the cosmological constant were much bigger than it is, then the universe would have gone through its expansion so rapidly galaxies and stars would not have formed. And in fact, you could calculate what would be the typical universe in which the cosmological constant is small enough so that astronomers would exist, weighted by the number of astronomers. And it turns out that our universe, the vacuum energy is a little low. You might expect it to be, 10 times larger or 5 times larger, but it's not a very unusual kind of universe from this kind of anthropic calculation. Now, does this make sense? I don't know. It makes sense only, it does make sense if there really are a variety of universes in which the cosmological constant varies from universe to universe. And that is the case in modern string theories. In fact, the number of these, quote, universes, each corresponding to a different solution of the equations of string theory, which are incidentally not really well understood, is vast. It's like 10 to the 500, a 1 with 500 zeros. So string theory provides a concrete realization of this possibility, as earlier certain theories of the origin of the universe, so-called chaotic inflation, had done, where the different universes are different parts of space-time. The picture is that the universe expands not like a uniformly expanding cloud of gas, but like water in a tea kettle where bubbles of steam are continually bubbling, and we're just one bubble that happens to be bubbling, and there are many others in different parts of the tea kettle. The tea kettle may be infinite. In fact, there may be an infinite number of these expanding bubbles. We can't prove that God never intervenes because the world is too complicated a place. But increasingly, as the centuries pass, we see less and less need to assume any divine intervention. The famous opinion expressed by the Marquis de Laplace to Napoleon when Laplace explained the working of the solar system according to Newton's laws, and Napoleon asked, where in this is there a place for God? And Laplace said, "Sire, I have no need of that hypothesis." Well, the big science in the form I've been describing it runs into competition not only from manned spaceflight, of course, or from other branches of science like solid-state physics or medicine or geology, but it runs into competition with lots of the other things our society needs government to adequately support. We need education to be supported at a level so that a teaching career will be attractive to the best graduates of our colleges, as it now isn't. Our passenger rail infrastructure and our internet access structure, even our bridges, are at a state which look very poor compared to their counterparts in Europe or East Asia. Our patent office is so undermanned it takes years to get a patent application approved. Our judiciary is so undermanned that it takes years to get a civil action heard. Our prisons are so undermanned that being incarcerated, the Supreme Court recently decided, in some states amounts to cruel and unusual punishment. Violation of, what is it, the Eighth Amendment. Our ports are insecure to terrorists, and many Americans go without adequate health care. These are all things that require government support. Now, for each one of the things I mentioned, there are plenty of advocates, just like I'm an advocate for big science. But we tend to get in each other's way. We tend to conflict with each other. I ran into an example of this, I'm almost finished, a little while ago, some years ago in Texas. I found myself sitting at dinner with a member of the Appropriations Committee of the Texas House. And she learned I was a professor at the University of Texas, and she began to tell me how she was enthusiastically supporting more funding for higher education. And of course, this wasn't something I minded hearing. And then I stupidly asked her, and I told her, I'm so glad to hear this. What are you planning as the revenue source to support this? And she blinked at me and she said, oh no, I'm not planning to raise taxes. We're going to take the money from health care. This is not what we need. What we need is for those of us who care about government support for all the things our society needs, to unite, to help shift the balance of our economy more away from private goods in the direction of public goods, where the real needs of our society are. The real needs of our society are not for more consumer electronics, but for education, healthcare, scientific research, and so on. And this means higher taxes, which is a hard sell in a time when an anti-tax mania has afflicted the American public. But it's only in this way that we can get adequate funding for all the things that our society really needs, for education, for healthcare, for infrastructure, and all the others, and also for science of all sizes. Thank you. Now I think it's cosmology that is in a golden age. For the last 15 years or so, it reminds me of what particle physics was like then, with a wonderful fusion of progress in theory and experiment relevant to each other. Since 1992, I think it's fair to say that the most exciting things that have been going on in cosmology, with the possible exception of the discovery of the accelerating expansion, have been in the area of studying the fluctuations away from the smooth Robertson-Walker expanding universe. Of course, astronomers have always been interested in the fluctuations. I mean, after all, what else are stars and galaxies? But stars and galaxies of fluctuations that have evidently gone beyond first-order perturbation theory. They are in the nonlinear regime, and so it's very difficult looking at them to learn things about the very early universe. But in looking at the cosmic microwave background, which we've been doing, looking at the fluctuations in the cosmic microwave background, which we've been able to do since the COBE satellite in 1992, and now increasingly with very large surveys of interstellar matter at large redshifts before it becomes nonlinear, I should say intergalactic matter at large redshifts, we're beginning to really have experimental data on fluctuations in the universe that ties in with theories of the early universe. We have paradigmatic theories of the early universe, starting with the work of Alan Guth, under the general heading of inflation. And we have our measurements of things that happened when the universe was a few 100,000 years old, which is what we see in the microwave background. But in between those two eras, there are a lot of things we don't understand at all. And how is it that we can interpret what happened in the very early universe in terms of things that happened when the universe was 380,000 years old? When there's so many things that happened in between, we don't understand. And the reason is that during most of the history of the universe, from well before the end of inflation, and here's my first U-graph, until relatively recently, by relatively recently I mean after nucleosynthesis and electron-positron annihilation at temperatures well below 10 to the 10th Kelvin, all the fluctuations that we actually observe had physical wavelengths that were outside the horizon, in the sense that the co-moving wave number, which is Q over A, where A is the Robertson-Walker scale factor, it's the thing that tells you how the universe is expanding, is much less than h, the expansion rate, A dot over A. And here is a figure. Q over A, when during inflation, when A is increasing exponentially, decreases exponentially, and then after inflation, A increases like about t to the half or t to the 2/3, so Q over A decreases more gently. On the other hand, the Hubble rate, H, during inflation is roughly constant. That's what makes inflation. You have an exponential expansion. And then after the end of inflation, H decreases essentially like 1 over T, which is faster than Q over A. So you have an early period when fluctuations are inside the horizon, and then they leave the horizon, and then for a long time they're, for a long time, even by our standards, they're outside the horizon, and then eventually they re-enter the horizon. Now, it's during that period when they're outside the horizon that all the things happen that we don't understand. The energy that was in the inflaton fields gets converted into ordinary matter and radiation in an era called the era of reheating. Baryons are synthesized, we think. The cold dark matter gets decoupled from other matter and radiation. There's the Rick era that Frank Wilczek talked about, when the chiral symmetries get broken. None of these do we actually need to understand if we want to calculate the fluctuations that we will see now, because they all happened at times when the wavelengths of those fluctuations were outside the horizon.